In this video, we will begin our discussion on nucleophilic substitution by first talking about nucleophiles. Sometimes you'll see nucleophiles abbreviated as NU, sometimes it'll have a dot to indicate there's a lone pair of electrons. But the quality of all nucleophiles is that they are all Lewis bases, meaning they have a lone E pair, they have a lone pair of electrons to do some kind of nucleophilic attack on a carbon center. They can be both anionic, meaning they carry a negative charge, or neutral. And we'll examine a couple different kinds of common nucleophiles you'll see in this class. So common anionic ones we'll see. We may see MOH, which gives us OH minus. This is called hydroxide. And the M is to indicate a counterion as a salt, so this would be KOH or NaOH or LiOH, any counterion, usually a first or second group metal, to counterion the hydroxide. So this is called a hydroxide. MOR, which would give us OR minus, is called an alkoxide. R meaning any kind of carbon chain. We can have M and then this structure like this, sometimes abbreviated as MO2CR. This gives us the anion like this with the charge on the oxygen. This is called a carboxylate. We can also have MSH, which gives us the SH anion, which would be a hydrogen sulfide. Or if we have MSR, giving us the SR group, this would just be called a sulfide. And other common ones we see are MCN, which gives us CN minus. This would be a cyanide. And some of these are polyatomic ions that you should recognize, such as CN minus. We also have MNN3, which gives us the N3 anion, which is called azide. So these are all anionic nucleophiles. And when we're talking about the anionic nucleophiles, we're talking about these guys here. These would be the nucleophiles that are doing the nucleophilic substitution on a particular ion, on a particular carbon center. Now the M would just be a spectator ion in this reaction. So this would be anionic, so this is anionic. We also have neutral nucleophiles, and these are often solvent. And if it's a solvent-based, if the reactant is the solvent, we call it a solvolysis reaction. So this is things like H2O, methanol, ethanol, acetic acid, which is this structure here. Ethanol would be this, methanol would be this, water is as written. Or something like ammonia. And keep in mind that all of these have lone pairs, so H2O has 2, methanol has 2, ethanol has 2, acetic acid has 2, and H3 has 1. So these are all Lewis bases, even though they are neutral nucleophiles. They could still do a nucleophilic attack. There would just be an extra step where, as we saw in Chapter 5, attack by H2O would form an oxonium ion. You'd have deprotonation, and you would proceed with the mechanism. Now what we see is that anionic nucleophiles are going to be stronger nucleophiles than neutral nucleophiles, meaning they are more reactive. And what we see in terms of nucleophilic strength is that the stronger bases are stronger nucleophiles. So if we were to write the halide series, we have F minus, Cl minus, Br minus, I minus. These could all be, these halides are all potential nucleophiles. we would see that F minus is going to be the weakest nucleophile, followed by Cl minus, followed by Br minus, followed greatly by I minus. And that's because I minus is the strongest base here. It's the most polarizable. It has the lowest the highest pKa, and it would be the strongest nucleophile in this case in this halide series. Now, nucleophilic substitution is a good way to, if we're doing, we're thinking in terms of synthetic possibilities. This is how we use to transform functional groups, which I'll abbreviate as FG. So transform or substitute functional groups. So for instance, if I have Br and I add NaOH, in this case we're adding a hydroxide, what we would end up with is a new functionality where we've created an alcohol and our counterion, or our resulting NaBr off to the side. So we've transformed an alkyl halide into an alcohol. And this is true for any type of substitution mechanisms. We're always going to transfer functionality from one thing to another. So say I add NaCN to this secondary alkyl chloride. Well, we transform this alkyl chloride into the cyano alkyl group, and we'd be left with NaCl at the end. Usually I would only be interested in the organic product, but this is just to balance the reaction. Just to show two more examples, say we have this alkyl bromide and we add potassium ethoxide. So again, this OET is going to be our nucleophile here. We'd end up with the transformation of converting the alkyl bromide into the ether in this case, and we'd be left with KBr. So we've transformed the alkyl bromide, we've substituted it with OET, and this functionality here is called an ether. One more example. Say we have a secondary alkyl iodide, and we add potassium hydrogen sulfide. As you can imagine, we're going to do the substitution reaction, and we're going to convert that alkyl iodide into the sulfide, or the hydrogen sulfide, and we'd be left with the salt of Ki at the end. So this is a good way to transform one functional group, usually an alkyl halide, into another functional group with diverse possibilities depending on what kind of nucleophile you're using.